Okay, so welcome everyone. I will just first introduce myself. So I'm Jelena Jankovic, a software engineer specialized in databases and system engineering. So I'm proficient in Rust, C, C++, and Python. I have hands-on experience in designing high-performance database engine, optimizing query execution, and building scalable storage for analytical and high performance and like large-scale data workloads. So my main passions are for data, databases, optimizations, in general system engineering, and low-level programming. You can also find me on LinkedIn if you want, but please stay in touch. And as you can see, we have today data-intensive systems in Rust. So this presentation aims to get you curious and excited about using Rust for modern data-intensive applications. I'll explain how Rust is changing the game and why, especially for analytics, high-throughput systems, and emerging data tools. So to start with, I would just like to bring some probably most of you are already familiar with these concepts, but just to provide some overview or background. So here we have a cache. So you can think about the CPU's cache as an ultra-fast, tiny memory that keeps recently or frequently accessed data close to the processor. So all data structures or algorithms, everything that fits into the cache runs dramatically faster than if we need to fetch data from main memory or disk. Then the next term is transaction. So transaction is a sequence of operations that are treated as a single atomic action. So either all of these operations happen or none of them. And that is when you work with databases or data, it is very important, especially with these SQL databases. We have these ACID things, atomicity, consistency, integrity, durability. So transactions are important for as a guarantee for correctness, even in the presence of failure. Then next terms are row and column stores. So those are just two ways of storing structured data, and I will talk about them in the following slides, as well as OLTP and OLAP. So these are acronyms for online transactional processing, which is usually used for fast updates, and online analytical processing, which is used more for analytical workloads. I will also talk about them later, but just yes, you can see them as OLTP or online transactional processing usually handles many small, quick transactions. You can think about shopping carts, banking, bookings, while OLAP is usually useful for handling huge complex queries for analytics or reporting. So you can think about dashboards or trend analysis, sales. So yes, at the end of this presentation, you would have time for questions. So please just keep them in mind or write them somewhere. So as the title of this presentation are these data-intensive applications. So in this slide, I would just like to bring you some intuition about these data parts. So just how the data flows. So data typically flows from raw ingestion through processing or transformation, and then storage, and then finally it is used for serving or in this query layer. Then you probably wonder why Rust for data-intensive systems. So there are some of the main data intensity challenges like memory, concurrency, latency. So memory-wise, Rust brings memory safety without a garbage collector. So no runtime surprises, no memory leaks, no data corruption. So Rust's ownership and borrowing prevents bugs like double freeze or data races, buffer overflows. So there are no surprise crashes at 3 a.m. with Rust. Then as well, Rust brings predictable performance, so bare metal performance. So you control how memory and data are laid out. Then it also provides safe, high-speed concurrency for parallel analytics. Rust has pretty mature data tools. So I just mentioned here some of them, like Apache Arrow, Parquet, Polar's Data Fusion. So they are pretty frequently used also by many developers. And it is also great that the ecosystem is growing. And Rust became very popular in the past years, which is also great. And what is also exciting is that this community energy. When I started 4 years ago working on my previous job with Rust, there were not that many people using Rust. So it is great to have a community like Women in Rust and also these other contributors to Arrow or Data Fusion, so that we can also share some experiences, knowledge, and hang out from time to time. Now, don't get scared with this slide here. I just want to provide you some background before we continue with the following slides. So just to give you a background of how the simplified database management system architecture looks like. So here we have some a front-end parts. So either web forms, application front-ends, or SQL interfaces, which use SQL commands. And then usually a SQL query, which probably most of you are familiar with. Like you can select something from some database, and then you can have some conditions or filters in where clause or general SQL query. And then that query gets parsed, optimized, then we get some query plan execution plan, but we don't need to pay attention that much on that part. In the following slides, I will talk about this data that is fed on a disk, that usually this query is applied against this data. So if we zoom into the storage, we just wonder how does this database management system store this data? And on this slide, you're probably familiar, if you ever used Excel or any database, you're probably familiar with this kind of representation where we have a student's table and then some attributes or columns, like here, student ID, name, login, age, GPA. But that is just a visual representation. All of this data is stored in some kind of storage and in files. Each file, so we have files in a storage. Each file contains multiple pages, and each page again contains multiple rows or tuples or records. Those are all synonyms. And each row is divided into fields. You can consider these fields as columns that we have here, for example, this SID, name, login, age, GPA. So the DBMS stores the data as one or more files on this. And that is important because in the following slides, we would focus on how this page, which layout can this page have? So in which layout can we store this data per page? So as I already mentioned, on this slide, you can see the two most popular data or page layouts, which are row store and column store. Of course, there are also hybrid versions, but we won't focus on them in this presentation. So to help you understand this better, here is again an example table, student. So we can see that student is described by its ID, name, age, and GPA. And here we can see three different students. And now we will see how these data can be stored on row or column store. See here, for example, in row store, all of the attributes are packed together. So rows are packed together in a page, which means that first we have data for one student, then for the next one, and then for the third. And this layout is usually convenient for online transactional processing workloads. That means these transactions, quick updates, inserts. If you wonder why, it is because we cannot lock, if we have this table and we want to update name, we cannot lock it by like row and column. We need to lock the smallest granularity is row-wise. So that is why it is convenient to use row stores if we have such workloads, like to do small updates on each of these fields. In opposite to that one, we have columnar store as well. And here we can see that we have a page per column. So we have one page for student ID, then one page for name, age, GPA. And we can see that each page contains all of the values for this attribute, but across all of the rows. And usually such data layout or page layout is useful for these analytical workloads, because these analytical workloads usually care about one single column or very few columns. For example, if we want to find all of students that are older than 18 years, for example. And what is also important to mention here, that there is no one size that fits all of the needs. So with these data layouts, it is very important to know which workloads should we expect, and then it can influence our decision if we should choose one instead of the other. So different workloads require different storage layout and, in general, data access methods. This slide, I would just like to provide you with a Rust example of row store. Here we can see that I would again emphasize that it is usually convenient for OLTP styled data, so for transactional workloads. And here we can see that each student is one row. And if we create collection of students, we can see that here we have like all of the attributes for each student. And then we can query it. It is pretty straightforward, I guess. So in this query, we want to find all students with GPA bigger than 3.3. And that is also what we verify here with assert equal. We just want to check that the first student from this best student that we choose here has the name Jones, which we can verify here as well. So our condition is that the GPA should be bigger than 3.3, and only this one, the middle one named Jones, satisfy this filter. Now we have also Rust example of column store. As we already said, it is convenient for OLAP style or analytical workloads, and we can see that each vector is a column of one attribute. So we can see that we have a vector for IDs, for names, then a separate one as well for ages and GPAs. And here we can also see how we store this data. Instead of having in one place all of the attributes per student, here we have, for example, all of the IDs in one place, then all of names, as well packed together. And in this example here, with a query to get all names where age is bigger than 18, it looks something like this with this like Rust iterator pattern. And as well, we use assert equal to verify our result. So if we want a student that is older than 18 years old, only the first one, which is Dave, satisfy this condition, and we can verify that our result is correct. Now to summarize, what is the difference between transactional and analytical workloads? So usually transactional workloads are small and frequent ones. Those are usually inserts and updates of a single row. As I mentioned, booking, banking are just like regular use cases, and row storage is more convenient for such workloads. While on the other side, we have analytical workloads, which are usually large and analytical. So when we use aggregates and scans of billions of rows, we usually rely on columnar storage, and yes, some of use cases are yearly trend analysis, sales, or dashboards, so that kind of use cases. Here is just like a simple demonstration of a query over columnar data in Rust iterator pattern as well. We can see that we have two structs, names and ages, and then we have collection of names and collection of ages. And if we want to get all names where age is bigger than 32, we can zip these two iterators and then just apply filter, get the name, and then again use assert equal to verify that filter data is the correct one. And we can also verify it by checking what we entered here. So if we want all the people older than 32 years, those are these two, which are Bob and Eve. So we can verify that our result is a correct one. Then what is also important with these large workloads is, and in general, what is usually frequently used in query optimization are these predicate or filter pushdowns in analytics. As we can see here, we have a query which is select name from some table where age is bigger than 32. And what usually many tools that are Rust-specific tools, like Data Fusion, that I would mention in our following slides, do is to scan, to filter while scanning the data. So if we have on disk these three, like age 30, age 40, age 35, it is better to, that if we apply filter, which is that this age bigger than 32, before the data is loaded. So this means that we reduce I/O for analytical workloads, which can bring significant improvement and optimization. So only data blocks that match the filter are read from storage. So that means that we push down the filtering. So if we do not support this thing, then we would read everything from disk, and then while iterating through data, we would decide which row goes through, passes the filter, and which one does not. Here I would mention also tools that are frequently used in Rust. Those are Apache Arrow and Data Fusion. So Apache Arrow is a standard columnar in-memory format or data layout. So it is also shared across languages like Rust, Python, C++. While Data Fusion is a query engine which is built on top of Apache Arrow, and it is used for efficient SQL execution in Rust. So Data Fusion is just a tool that you can, is a query execution engine. So if you want to build something customized, you can rely on Data Fusion, and it allows you to just plug in your custom logic. And as we mentioned, predicate pushdown in Data Fusion. Here I just provide one example to show you how it can be done in Rust with Data Fusion. We can ignore these parts. So for Data Fusion, it is also important to provide the source of data. In this example, it is just like a Parquet file. It can also be a CSV one. I just chose this one to make it like less lines of code so that it fits better in this slide. And then here we can see that Data Fusion automatically applies predicates at the scan level for efficiency. So only matching rows are read and processed, which is important here. So if you want rows where age is bigger than 32, then just like Rust engines like Data Fusion can skip disk blocks that don't match. This speeds up analytics hugely for big data sets, and we can see here. So example is pretty straightforward because we already had similar ones on previous slides. Then in this code snippet, I just want to show you how you can just plug in your custom logic to Data Fusion. So Data Fusion has these like UDFs, which are user-defined functions, where you can add it has also SQL syntax, but you can add your custom logic wherever it is needed. So as we can see here, I'm just creating like a table of these elements here. So A is just an array which contains 2, 3, 4, 5, while B is second array which contains 1, 2, 3, 4. It is not used in this example directly, but it is here to let you see that like a table structure easier. And then we create batch. Batch is like a table. So Apache Arrow has these record batches. So it is just like a data per column. Yes, it is like a table of a single column, like a slice. And then so we work on this data. And here we want to create our own custom user-defined function which would double integer values. So if we provide value A, it would just do A times 2, as we can see here in this example. And what is also very important is how do we incorporate it into the Data Fusion. Data Fusion provides this create UDF function where we specify the name of our user-defined function, which is in this case my double, then argument types, and then as well return type. And we have this volatility immutable, which means that it just tells Data Fusion that our user-defined function is deterministic and side effect free. So it is also enabling better optimizations and execution performance. And then when we register our user-defined function, we can see here an example of usage. So now we are able to do select my double A from some table. Here it is, we called it T. And yes, we just gave an alias like doubled. So whatever we add as our custom logic, we can then make it SQL accessible, which is very important. Now let's talk a bit about performance tuning patterns. So with Rust, we have this zero copy deserialization, which is important because it avoids copying large amounts of data and as well reduces memory allocations. So Rust is able to just like reference input binaries without needing to copy everything. Then as well, it is like a suggestion to use inline always for hot paths. So hot paths in Rust are the sections of code that are executed frequently or form the critical path of performance in your program. And with this flag, if we write inline always above our function, that is a hint to compiler. It is like telling a compiler, please copy this function's code at every call site for speed. Then as well, if we want to profile or benchmark, we can use criterion and perf and flame graphs. So criterion is usually used if we want, for example, to check the performance of two algorithms. Then we can compare two different executions. And then we get like a comprehensive benchmarking like statistics, while perf is Linux-based tool. So it is more on a side to check like it is more like a CPU profiling tool. It gives us an intuition where we spend the most time or what are the bottlenecks in our program. And it is also important to know different data structures and how do they behave, how do they allocate memory. So that can influence our also like which one to choose and how does it affect cache and in general throughput. So as I mentioned here, pro tip is profile first and then optimize last, because we need something to focus our optimization. So we need first to see where we spend the most time in, for example, query execution. So to see what is the bottleneck and then optimize later. Yes, and as I already mentioned, Rust has pretty mature ecosystem. So Here I just decided to put 3 of the most used tools that I use professionally. So Data Fusion, Serde, and Tokyo. Data Fusion, as I already explained, is a modern SQL query engine built in Rust, which relies on Apache Arrow for fast in-memory columnar analytics. And I provided here an example that you can use Data Fusion to accelerate ad hoc analysis, queries for millions of records, running custom predicates and expressions from within Rust. So what is important here are these millions of records and custom predicates as well. So it is pretty flexible. So Data Fusion allows you to attach your custom logic on like pretty much throughout the whole stack that it provides. Then as well for serialization and deserialization in Rust, we have this Serde crate, which supports different it supports JSON, YAML, CSV, I think Avro as well, and many more. It keeps APIs and data pipelines simple and safe. Here I also provided just a use case example. So you can, like using Serde, you can build a robust ETL. ETL is acronym for extract, transform, load. Usually something that you do before you fed your data into the database as a storage. You just need to clean it or transform it in a structured way. Yes, and every data transformation error is caught at compile time or handled gracefully. Then for all of the async stuff, if you would face them, then you would probably use a Tokyo, which is an async runtime enabling scalable network servers, APIs, or streaming data pipelines. And for each of them, if you would need them, then you can just dive deeper. So it is important just to summarize that the Rust data ecosystem is vibrant, rapidly maturing, and packed with powerful libraries and tools for data engineering. And whether you need analytics, a search engine, or embedded machine learning, there is almost always a Rust crate that is ready for production. So then as well, if you're thinking about different migration strategies, or you have some code written in some other programming language and you question how can you bridge it to Rust, or some parts of it rewrite in Rust for optimizations, then usually suggestions are that you should start with one data heavy or critical path module in Rust, so that you just like, it is called like stepwise replacement. So you can start by rewriting hotspots, critical or slow modules in Rust, while keeping the rest in legacy code. Yes, and here I just provided an example that you can replace a data transformation step in a Spark-like pipeline with Rust for 5 to 10 times speed gain. Yes, this is important if you work with large amounts of data, and if the data is also distributed, then you would probably get familiar with Apache Spark as well. And to wrap up this presentation, let's just check again the final takeaways about Rust. So Rust brings control and safety. So it is perfect for data systems. Rust strong typing makes both row and column stores ergonomic and safe. It has composable API, so Data Fusion allows you to build and extend analytical engines without knowing Data Fusion internals, which is also very important. So you don't need to go deeper into Data Fusion internals. It just provides you with the API, so you can just plug in your custom logic. Then again, strong ecosystem and open source growth. And if this triggered your mind, you can always do an experiment. You can write a few lines of Rust, of course, incorporating some SQL there, and then you can run it on large data and see production grade speed. And then probably you would rethink or not question yourself more. And if you work with systems and you care about safety and performance, you should probably already switch to Rust. And if this triggered your mind, and if you feel ready to try some Rust, I provided here some resources that I found useful. So it is always useful to check what other women in Rust are doing through this community here and talks. Also for beginners, Rust book is very useful and starting point always. And then when you get more advanced with Rust, I suggest by heart this Rust for Asterians book and John Gangset YouTube channel. So if you need something more advanced and more into details in Rust and you cannot find it anywhere, then probably his channel would solve your issues. But be ready that his videos are not small ones, so you can expect like 1, 2, 3, 4 hours of like deep diving into Rust. So highly recommended. And then as well, Data Fusion, Apache Arrow, those are just like tools that provide great docs. So whatever you need, it is well documented there. Thank you very much.